Hey folks, this is the optional lesson on implicit differentiation. This is not technically part of the MCV4U course, but it can be a helpful tool to have. And if you are interested in taking the AP Calculus exam, it will definitely be covered there. So first of all, looking at what the difference between an explicit and an implicit function is. So an explicit function is the type that we're used to seeing, having something that's y equals or f at x equals. That's the normal kind of function we're used to seeing when we're doing, especially when we're doing derivatives. An implicit function can be sometimes the same function written a different way. That's where it's not written in terms of one variable. So it's not written as the dependent variable being equal to something, like not a y equals. It's just a different relationship between two variables. So if we had this function y equals x squared, we know that when we do the derivative of that it's 2x. But the chain rule is still applying here because we would just be looking at this x as the inside function. So we're doing the derivative of something squared, which is 2 times that same thing, times the derivative of, that's what I always say is like the inside stuff. In this case, though, if it's just an x, we know that the derivative of the inside stuff is just 1. So we don't actually write that every single time. So here, if you've got y equals x squared, dy dx is 2 times the inside stuff to the exponent 1 times the derivative of that inside stuff, which is just 1. Because this is so common, we don't end up writing that multiplying by 1. So that's the derivative of x every single time because it's always 1 and you don't need to bother, and we just kind of skip over it, but we really are doing it. And that's what we're going to need to think like when we're doing the derivative of some implicitly defined functions. A different way of writing this is using the chain rule in Leibniz notation. We have dy dx is the derivative of y in terms of u. So the derivative of the outer composite function, keeping that inside function the same, multiplied by the derivative of the inside function in terms of x. So we will take a look at a kind of standard chain rule question here. So doing this the normal way, if we said y equals 3 plus 7x to the exponent 5, dy dx, if we use the chain rule, it would be 5 times 3 plus 7x to the exponent 4 times the derivative of that inside stuff, which would be 7. Now we are doing this, we're doing the chain rule, and we are sort of thinking of that inside stuff, that 3 plus 7x, as a separate function. And usually we write that as like f at g at x, but it can also be written as a substitution in terms of u. So if we let u equal to that inside stuff, we can say that y is equal to u to the exponent 5. And then the derivative of y with respect to x is the derivative of y with respect to u. And we would see dy du here as being 5u to the exponent 4 times the derivative of u in terms of x with respect to x, du dx, if u was just that 3x plus 7, that would be 7. And if we did a substitution back in, so we knew dy du was 5u to the exponent 4, and du dx was 7. then dy dx would be would be 5u to the exponent 4 times 7. And if we substitute back in what we know u is equal to 3 plus 7x. So if we sub back in, we get the exact same thing as if we had done it the regular way using the chain rule. So what we're going to do now is look at an implicitly defined function and do the same kind of idea to find dy dx. So we've got this function here, y squared plus x cubed minus y cubed plus 6 equals 3y. This function we would not be able to take the derivative of in our traditional manner because we can't get it explicitly defined. We can't get it defined as a y equals. That is a very, very difficult equation to try and solve for in terms of y equals something. So what we're going to do is take the derivative of each term. So taking a look at each of these individual terms of the function, we're going to take the derivative without rearranging it and just take the derivative of each term individually, but remembering to use that chain rule if we know y is a function of x. So we're going to have to include a dy dx when we take the derivative of that outer function involving y, just like we had to multiply by du dx. So here we're going to take the derivative of y squared. So the derivative of y squared is 2y, but that we know that y is a function of x, so we would have to take the derivative of the inside stuff. Even though we don't know what that inside stuff is, we know that we would have to take the derivative of it if we did the chain rule here. The next piece, we're going to take the derivative of x cubed. So the derivative of x cubed we know is 3x squared. And I'm actually going to show this. I'm going to say this is the derivative of x times the derivative of x with respect to x. I know that that's equal to 1. Okay, I'm not always going to show that every time, but just to kind of show you are actually doing the same pattern here. Then the derivative of y cubed. The derivative of y cubed is minus 3y squared, but y is a function of x, so we are going to have to take the derivative of the inside stuff. We don't know what the inside stuff is, so we just write dy dx knowing that that would have to be multiplied by that derivative. The next piece is the derivative of 6. The derivative of a constant, of course, is just 0. Equals, and then the derivative of the 3y is 3, but we know that y is a function of x, so we would have to use the chain rule and do the derivative of the inside stuff. So cleaning this up a little bit more, we know that the derivative of x in terms of x is just 1. I normally will not show that. I just kind of showed it there to show that you always are doing that chain rule, but when it's just an x, we don't show it every time because it is just the 1. So then I would have 2y dy dx plus 3x squared minus 3y dy dx. I'm not going to include that 0, equals 3 dy dx. So what I want to do here is to solve for dy dx. I want to find the derivative of this function y in terms of x. So I'm just going to do some algebra here and isolate it. So I'm going to bring everything with, oops, this was a 3y squared. I'm going to bring everything with a dy dx to one side and everything without it, which is just this 3x squared term, to the other side. So here, 2y dy dx minus 3y squared dy dx minus 3 dy dx equals negative 3x squared. Common factoring a dy dx, I get 2y minus 3y squared minus 3 equals negative 3x squared. And then solving for dy dx by itself, I'm going to divide out that bracket on the other side. So I get negative 3x squared over 2y minus 3y squared minus 3. So because I can't solve for this function in terms of y, I can't get a derivative just in terms of x. But if I knew a point on this function or relation, I shouldn't say function because it may well not be a function. If we could find a point on this graph or a point that satisfies this equation, and we knew both the x and the y value, then we could find the rate of change of the y in terms of x at that point. So to find the actual, to find dy dx at a point, you need both the x and y. Not just the x value like we do when we have a function that's defined explicitly. So similar kind of question here. We've got this other relationship, 5x cubed plus xy squared plus 5x cubed y equals 5x cubed y cubed. So we're going to take the derivative of each term with respect to x. When we're doing a derivative of a piece of this equation with an x in it, I'm not going to write the dx, but we know that it would actually be there. So I've got more space over here. So the derivative of the first term, I have 5x cubed. So the derivative of 5x cubed is 15x squared. Good stuff. I don't have to write dx because we know that it's just 1. The next term has a little bit of a twist. This is going to need the product rule. Because we have an x and we have a y squared. So I'm going to have to look at this as a product rule. So I'll put plus, and then I've got the first term, x, times the derivative of the second. So the derivative of y squared is 2y dy dx. Plus the second term, which is our y squared, times the derivative of the first. The derivative of x is just 1. So you could have to do product rule or quotient rule in conjunction with this implicit differentiation. And if I look on the other side of the equal sign, I have something really similar. I'm going to kind of group the 5x cubed as one piece, the first factor, and then the y cubed as the second factor. So here again, I've got the first thing, so 5x cubed times the derivative of the second, which is 3y squared, but now I have to do the derivative of the inside stuff, so dy dx. Then plus the second factor, y cubed, times the derivative of the first, which is 15x squared. This is not times dy dx because I didn't take a derivative of the y piece. I only had derivative of x, so it would be dx dx, which we don't write at the end. You can write it, but it simplifies things if you don't, okay? So cleaning things up, I've got 15x squared plus 2xy dy dx plus y squared equals 15x cubed y squared dy dx plus 15x squared y cubed. So again, you want to be able to solve this for dy dx. So I bring the terms with a dy dx all onto one side, and then the terms without over to the other side and isolate and solve. So I have 2xy dy dx minus 15x cubed y squared dy dx equals 15x squared y cubed minus 15x squared minus y squared. And then common factoring out the dy dx on the left. And then we'll divide out that bracket. So dy dx, the simplification and solving for dy dx is very similar every time. So 15x squared y cubed minus 15x squared minus y squared over 2xy minus 15x cubed y squared. So they do get a little bit big. You may need to look at the derivative here with the product rule. You could get one for sure with quotient rule. That would be kind of similar. You just remember when you're doing a derivative that's in terms of a y value, you have to multiply by the derivative of y in terms of x, even though you don't know what the y function is. So we don't actually know what the inside stuff is or its derivative, but we just know that the derivative of the inside stuff would be there even if we don't know what it is. And that's what we end up solving for.